Hello and welcome to Chapter 17, where we're going to be taking a lot of information that we saw in Chapters 15 and 16 and applying them even further with these acid-base theories. And so particularly in this chapter, we're going to look at buffers and we're going to look at titration problems. Titration you've already looked at in Chem 1211, but this is going to be a more sophisticated type of titration where we're going to be focusing more on pH rather than a colored indicator. So it is a little bit more exact when we're working with a pH titration. And so hopefully you'll get a chance to do that in the lab as well and see the difference that it makes. We're going to start off by talking about buffers. And so a buffer is a solution that has a weak conjugate acid-base pair. So that's something that's very important for you to recognize. So a buffer will always be made of a weak acid and its conjugate base. So be aware of that. That's how you can determine that what you're looking at is a buffer, if it's just a weak acid and a conjugate base put together in a solution. And the main purpose of a buffer is that it resists drastic changes in pH. So this is extremely important, especially when you're dealing with biological samples. I mean, our bodies are filled with buffers to make sure that no certain part of our body gets out of its supposedly normal pH range. And so why can we say that it's a stable substance? It's because it contains both an acid and a base. And due to containing both an acid and a base, this means that it is able to neutralize any reaction. So if acid is added to our solution, is added to our buffer, then the conjugate base is going to react with it to neutralize it. If any base is added to our buffer, then the conjugate acid is going to react and neutralize it. So either way, we're going to be making water, which is going to help simplify things. And then we'll make either an acidic or a basic salt, and that only changes the pH ever so slightly. So let's take a look at what this really boils down to. And it all has to do with this idea of the common ion effect. And remember, this strange little symbol is supposed to be an arrow. So the common ion effect essentially is looking at Le Chatelier's principle, but for acid-base reactions. So a common ion is just any ion that was put into the solution, and the solution already had that ion in it. So it's like having a solution of hydrochloric acid. We know that hydrochloric acid, for example, is going to dissociate into H plus and Cl minus. So if we have that HCl solution and we add NaCl, we know that NaCl breaks down into Na plus and Cl minus. So now we have a common ion. We have chloride that's coming in from the sodium chloride, and chloride was already present in the solution because of the HCl. So because of this, it's the same thing that we saw with Le Chatelier, where if we were adding more of a substance, then we're going to expect it to shift away from that substance. So again, if we are adding a common ion, the reaction is likely to shift away from that common ion. So let's take a look at the example that's here with acetic acid. And so the common ion effect is usually looked at with weak acids because they partially dissociate, and strong electrolytes. So the common ion effect is most often used with weak acids plus a strong electrolyte. And that's how you'll be able to identify that the common ion effect is occurring. So here we have a solution of acetic acid. We know that in acetic acid with water, it's going to dissociate, and it's going to only partially dissociate. So actually there should be the equilibrium arrows here. And it'll partially dissociate into acetate and hydronium. So let's say, for example, if we added sodium acetate to the solution, which way will the reaction shift? If we're adding sodium acetate is a strong electrolyte. So it's going to break down, if it's Na CH3 COO, it's going to break down into the sodium ion and the acetate ion. So what we just did is added more acetate to our solution. So since we're adding more acetate, we're going to expect our reaction to shift left. And this is really important for us to understand, because that means that our ionization is going to decrease. So by us adding in more of the conjugate base, we're decreasing the amount of acid that dissociates, which means we're going to change the pH as well. So we can see that hydronium is what we use in order to find pH, right? We learned about that in chapter 16. So if we're shifting to the left, we're shifting away from the hydronium, which means that our hydronium concentration is going to decrease. Concentration decreases, which means that our pH then is going to increase. So this can play a large role on the solution in question if we have a common ion present. Again, this is just Le Chatelier's principle, but looking more specifically at what happens with weak acids and bases. So this idea is really just what's happening in a buffer system. And so let's take a look at what that looks like. Now, most of the time, when we're dealing with a buffer solution, when we're making a buffer solution, we like to have our acid and our base in similar concentrations. The way that buffers are usually made, or a way that is most simplistic for us to make buffers, is to make the acid and base concentrations equimolar. So equimolar just means equal molarity, equal concentration. Does that mean that a buffer has to be equimolar? No, it does not. It's just the most common way of making a buffer. And like we said before, since this contains an acid and a base, if we add a strong base to our reaction, then the acid from the buffer is going to react with it. So here's what that would look like generically. We added in a strong base. So we're adding in hydroxide. The hydroxide is going to react with our weak acid from the buffer. So again, the hydroxide is added. The HA is the weak acid that was already present in the buffer. And so when this acid and base react, we're going to make H2O, because the H from the acid moves over to the hydroxide to neutralize it, plus A minus. And so here is our conjugate acid-base pair that we said is present in every buffer. So we're using the acid portion of the buffer to neutralize the base, and then we're going to be left over with some of our base from the buffer system. That's going to be a common ion. Okay, just to kind of tie it back to what we had just discussed. If we're dealing with strong acids being added to our buffer, then the base portion will react with it. So in this case, we're going to have H3O plus reacting with the conjugate base of our reaction, of our buffer. So again, H3O plus is what's being added to the system. A minus is the conjugate base that was already present in the buffer. So hydronium is going to give away its proton. We're going to make water again, plus our conjugate acid that's in our buffer. So again, we have our conjugate pair that was already present in the buffer, and that's how we're able to keep this pH relatively stable. Now, these two examples are really good generic formats for you to write an equation reaction for any type of buffer and for any type of acid or base that is added to it. So it's important, or it could be good for you, to have these two equations memorized in the blue and the red, so that when you're dealing with any type of problem, it doesn't matter what the acid is, it doesn't matter what the base is, it doesn't matter what's in the buffer, you can write out this generic equation and it's going to work the same way that you need it to, regardless of the identity of the substances in the buffer system. So let's look at how we can find the pH of a buffer. So just because a buffer helps keep pH simple and it isn't changing, it's stagnant, that doesn't mean that the buffer itself automatically has to have a pH of 7. That's usually not the case. A buffer can have any pH, and it helps keep the system at that pH. So in order for us to find the pH of a buffer, we use something called the Henderson-Hasselbalch equation, which I'm usually just going to call the HH equation. Now, in an acidic buffer, which just means that the pH of the buffer itself is acidic, we have this equation that the pH is equal to the pKa. So remember, Ka is the acid dissociation constant. P means the negative log of. And then plus the log of our base concentration. So I'm just going to call that B for base over our acid concentration. And again, I'm just calling that A for acid. Now for a basic buffer, which means again that its pH is going to be basic, we can use something different, slightly different, but this is the equation that you're going to see most often. So I want you to be familiar with this one. It works for basic buffers as well. but it's technically considered the acidic buffer Henderson-Hasselbalch. So remember, if you're given an equation of something that's basic, we can go back and forth between Ka and Kb in order to plug into this particular equation. So remember from chapter 16 that Ka times Kb equals Kw. So if you're given Kb, you can just find Ka and then plug into your equation here. So let's say we have a buffer made up of a concentration of benzoic acid and sodium benzoate. So sodium benzoate and benzoic, those are your conjugates, and we're given the Ka of the acid. Now I do want to note, though, that when you're dealing with the Henderson-Hasselbalch equation, you can either use molarity for your concentrations, or you can use moles. Because we're dealing with the same solution, your volume is going to be the same. So your concentrations of B and A can either be in molarity or moles. So in this case, we're given molarity, so we're just going to stick with that. So the pH of the buffer equals the pKa. So P means negative log. So we're taking the negative log of 6.3 times 10 to the negative 5. And the pKa is 4.2 plus the log of our base over our acid. So the base is the sodium benzoate, so 0.2 over the acid is 0.12. And you'll notice here that we don't have equimolar amounts of our acid and base. Again, that is okay. And when you're actually making a buffer, this is common for them to be a little bit different because you want to get to a specific pH. So usually when you're working in the lab, you know that you want a pH buffer of 5. And so you have to manipulate a little bit in order to get to 5. So it's possible that you won't have equimolar amounts, but you could. And ideally, you want to be relatively close. So in our calculators, we can type in this equation. The way that I'm going to type it into my calculator is I'm going to do 0.2 divided by 0.12 first. So I get 1.666667. And then take the log of that. So I get 0.2218. Add 4.2. So my final answer, the pH of the buffer system is 4.42. And remember, for pH, we don't have any units. So this is just looking very simplistically at a buffer, nothing added to it yet. But as we saw earlier, the whole point of us having a buffer is that we can add substances to it and hopefully not change the pH too drastically. So how do we determine what's happening there? Well, we know that buffers counteract additions, meaning if we add in a strong acid or a strong base, we know that the buffer will neutralize what is added. So in chapters 15 and 16, we used ice tables. Here, we're going to use something called a BCA table. So you set it up BCA. Again, you're going to have your chemical reaction up at the top. One of the two generic equations that we wrote out a few slides back. And so B stands for before. So it's essentially the initial portion of your chart. C stands for the change still. And I apologize, my pen, I just recalibrated it and it seems to be acting funny on Blackboard, so hopefully you can read what it is that I'm writing. And then A stands for after. So before, change, and after, just like we had initial change and equilibrium. The difference between a BCA table and an ICE table is that BCAs are done in moles. ICE, remember, has to be in molarity or pressure. But for these types of problems, we're starting with one volume and then we're adding acid or adding base to it. So we're changing our volume, which means that our concentration is going to change. So we want to just look at the moles first, and then we're going to take into account the new volume that we have. Now, one other thing that I want to point out is that A, for the added piece, so that's usually the strong acid or the strong base that was added to the buffer, will be 0. So A at the end of our reaction should be 0, because again, the point of a buffer is to completely consume whatever is added and help neutralize it. So A for whatever's added will always be 0. Remember, we can ignore water because water doesn't matter in an equilibrium anyway. So let's take a look at why we even use this type of BCA table. Why we need to figure out what the pH change is if the whole point of a buffer is to keep the pH relatively stable. Why would we have to use a BCA table to see what the new pH is after adding something to it? Well, it has to do with this idea of buffer capacity. And so buffer capacity is the amount of acid or base that the buffer can neutralize before the pH changes a considerable amount. So what is considered a considerable amount? That just sounds like a very relative term. Well, buffer capacity is usually plus or minus 1 pH from the pH of the buffer. So we saw in an earlier problem, we practiced with benzoic acid, and the pH of that buffer was 4.42. So the buffer capacity is we can raise the pH by adding base to 5.42, or we can lower the pH by adding acid to 3.42. So its buffer capacity here is from 3.42 to 5.42. Once we reach outside of that limit, that means that we no longer have enough of the conjugate to neutralize anything that gets added. So once we've hit buffer capacity, we no longer have something to help neutralize what gets added, so our pH is going to change drastically now. And what we mean by drastically is it'll go from, if it's at the 5.42, it'll shoot up to 11. And so obviously that's really bad. We have to make sure that we're not using our entire buffer. So buffers do break is the terminology that we use. Don't break the buffer, which means don't go outside of the buffer capacity. So in order for us to make sure that we're staying within the buffer capacity, we need to determine how much and what type of buffer needs to be used. The way you determine the buffer that needs to be used is by looking at the pH of the solution that you're trying to make. If you want to make a pH of 5, then you need to find an acid that will give you a pH of roughly 5. How do we do that? Well, you want to use an acid with a pKa close to the desired pH. So we see that the pKa for benzoic acid a few slides back was 4.2. So benzoic acid could be a really good buffer if you wanted the pH to be 4, for instance. How do we determine how much we need of each component? We use the Henderson-Hasselbalch, or the HH equation, to determine that. And so what we do there is we create a little bit of a substitution type of problem. So let me show you what that looks like. Let me pull up a blank screen. So let's just keep going with benzoic acid then, just because we have an example. Let's say that you want to make 100 milliliters of a buffer with a pH of 4. And so you've decided to use benzoic acid because benzoic acid has a pKa of 4.2, which is what we found in that earlier slide. So how do we determine how much of our acid we need and how much of our base we need? Well, let's say we're using a concentration of 0.5 molar benzoic acid and 0.25 molar sodium benzoate. So again, those are our conjugates. And we have in our hands or in the lab a solution of benzoic acid and a solution of sodium benzoate. In order for us to create our buffer, we need to mix those two solutions together. But we need to mix them in a very specific way. So we can start off by writing our HH equation. Right? We said that we want our pH of the buffer to be 4 equals the pKa is 4.2 plus the log of our base over our acid. So we're just going to leave base and acid alone because we are trying to figure out how much of each of those we need. Okay, so here we can get the ratio of base and acid by itself. So we're going to start off by subtracting 4.2 from each side. So that will give us a negative 0.2. Oops. So equals the log of our base over acid. And how do we get rid of log? Remember, we use 10. And in the past, we've taken 10 to a negative number, but that was because we were using a negative log there. Here we're using plus log, so we don't have to include a negative when we're raising. So it's just 10 to whatever number it is. So we happen to have a negative here on our left side, which is fine. So we're going to do 10 raised to the negative 0.2. And I get 0.631. And that is equal to my ratio of base over acid. Now let's think about what this number means really quick. If the number was greater than 1, that would mean we would need more base than acid, because base is in the numerator. Here we have 0.631, which is less than 1. So we're going to expect to have more acid than base. This makes sense because we want the pH of our solution to be more acidic than the pKa. Right? 4 is more acidic than 4.2. So then the question becomes, okay, well, I know that that's the ratio I need, but how do I figure out how many milliliters I need? Well, we know that when we add our acid and a base together, we want it to equal 100 milliliters. So now this is the type of mathematical problem where we have two equations and two variables. So what we do here is we need to look for a substitution. So how can we substitute? Well, my personal preference would be to rearrange this equation. So if I rearrange that, for instance, I can multiply by A on both sides. And so that will give me 0.631A equals B. Now that I have an amount for B, I can plug that in up here. So it's A plus 0.631A equals 100. So we combine like terms. Technically, the first A that doesn't have anything else written with it has a 1 in front of it. So 1A plus 0.631A gives us 1.631A equals 100. Again, all I'm doing is adding my like terms. So to get rid of A, or sorry, to find A, we can divide by the 1.631. So 100 divided by 1.631 gives us 61.3. So this tells us that in order to make our buffer, we need 61.3 milliliters of the acid, which is the benzoic acid. So then to find B, we can just plug that back into one of our equations. So we can plug that in and say 61.3 plus B equals 100. So 100 minus the 61.3, we need 38.7 milliliters of the sodium benzoate. And that's how you determine how to make your buffer. So again, a lot of these factors can change. It just depends on how much of the buffer you want to make, what pH you want your buffer to be at, and then you can go ahead and solve for how much of each buffer you'll need. And then once you know the amounts, you can figure out making your solutions because you know that it's a molarity and you know your amount, so you can find your moles. So let's go back and look at tying this all together. Let's try out a problem where we're adding a strong acid or a strong base to our buffer. So here, we want to know what is the pH of a solution that results when 0.3 moles of sodium hydroxide is added to 500 milliliters of a buffer containing 0.8 molar acetic acid and 0.04 sodium acetate. The Ka of acetic acid is 1.8 times 10 to the negative fifth. Assume no change in volume upon the addition of sodium hydroxide. So we need to set up our BCA table. And again, write out a generic formula. It'll make things a little bit easier for you. So just to make sure that I have enough room, I'm going to switch over to a blank screen. And let's write out what we know. So like I did with the ICE tables, we'll write out what we know in black, what was given to us in the question. So we were told that we were adding a strong base, so that's going to be OH, plus the OH, remember, is going to react with the acid in the buffer. So we can write generically, it'll react with HA, instead of having to write out the formula for acetic acid every time. And so we know that these two will react to make H3O plus, or sorry, H2O, thinking too far, plus our conjugate base. Okay. Now we set up our BCA. We know that water is not important, so we just have to fill in for these three substances. So we're told that we're adding 0.3 moles of sodium hydroxide. So we're going to put our 0.3 right here. And then we were told that we had a buffer containing a 0.8 molar acetic acid solution. Well, remember, in a BCA table, we need to use moles. So we were told it was a 0.8 molar HA and a 0.04 molar A minus. And we were told that together these are 500 milliliters. So we can find our moles because we know that molarity equals moles per liter. So 500 milliliters is equal to 0.5 liters. So 0.8 times 0.5 means that for our acid, we have 0.4 moles. And for our base, it's 0.04 times 0.5. So that is 0.02. And so again, we know that after this reaction has occurred, for any BCA table, the A of the added component is going to disappear. So A is going to be 0 for our hydroxide. And this is all of the information that we know thus far. We want to find out what the new pH is after this neutralization has occurred. Well, let's take a look at this first column. If B is 0.3 and A is 0, that means the change has to be 0.3. So for our reactants, we're going to subtract 0.3. And for our product, we're going to add 0.3. So it's the same thing we saw with an ICE table, minus X plus X. But in this case, it's very easy for us to find what X is. So that means for HA, it's going to be 0.1 molar. For A minus, it's going to be 0.32 molar. And so now we can figure out what our new pH is by plugging in our afters into the Henderson-Hasselbalch equation. So pH equals pKa. We were given the Ka from the question. So we take the negative log of the Ka, which was 1.8 times 10 to the negative 5, and that gives us 4.74. Plus the log of our base over acid. And again, we can use moles in this Henderson-Hasselbalch equation. So our base is the 0.32. Our acid is the 0.1. And so we solve for our pH. And we get a pH equal to 5.25. And you can always ask yourself, does this answer make sense? Would we expect for our pH to increase? And the answer is yes, because we're adding hydroxide, which means that we're making more of the conjugate base. So if we're making more conjugate base, we're expecting our pH to get more basic, to increase. So this is a good sign that we're on the right track. So the remainder of chapter 17 is going to look at titrations, and we'll do that in another video.